Hello, and once again, welcome to the last program, last lecture in this 15-day physical science program for class 10, mostly meant for our vernacular medium, Odia medium school. Don't be surprised, it was meant for Odia medium schools, but I'm speaking in English. That is an irony, but let's try to bear with this irony because I will send off my boys and girls with enormous confidence that you can, in your life when you go into +2 and then make your forward journey as a professional in engineering or medicine, whatever, you grow with full confidence. And let me tell you, our program for class 8 and 9, those who are watching directly from the YouTube, for them and for you also, Ipsita, welcome. You were not seen before, but better late than never. Anyone is welcome to the Zoom as well as for the distance viewing program. The class 8 program will start from June 1st, 1st, 2nd, 3rd, 3 days. And you know, when it is for class 8 and 9, I will be conversing with rustic, though not caustic, rustic Odia, because they can't follow, in English as you are doing now, because my gut as well as my heart says that you are accepting every word that I am producing here. That gut feeling is making me confident to speak in English. There is a telepathy which is working between you and me, that you are understanding what I'm saying, because I'm talking slow, not fast. Had I talked fast, then it would be really, really difficult, not for you alone, but for me also. When a native speaker speaks fast, then it becomes extremely difficult to catch everything what he or she is talking. So when you talk slow, it's easier for the other person to understand almost 100%. So in the last program, first class, let me share my screen and make a correction, which very painfully Mr. Paul has pointed out. He is a master in all these things. So the master has pointed out a mistake that I had committed while writing. Seaborgium is not SB. SB is antimony is here. It is SG. So by mistake, I had done this error. So the sooner it is corrected, the better. SG stands for Seaborgium, not SB, right? Mr. Paul, thank you very much. I think Jyoti means Jyoti Ranjan Paul. You would have written in Zoom. How did you go to the YouTube chat box and wrote there, not here? Had you written here in Zoom chat? Oh, okay. Thank you. He says I had written also in the Zoom chart, but I didn't see it. So again, thanks. A big thanks to you. Let's now, I think you have completed all the atomic numbers. Raise your hands who have completed these missing portions from 21 to 30, from 39 to 48, from 72 to 80, and from 104 to 112. Yes, you do that. Now I have already told, and then start a staircase below boron. Make these lines very, very bold faced. The stair steps will start from boron, below boron, one horizontal, one vertical, then one horizontal, then one vertical. So put a bold line to demarcate the non-metals from metals. This is a hypothetical staircase which is drawn in the periodic table in the long form to separate the non-metals from metals. It starts below boron, one horizontal, then one vertical, one horizontal, one vertical, horizontal, vertical, and finally it ends here. You don't go below because polonium is a very, very scarce element and radioactive, though natural. So it's though metal, but we forget about polonium. It's a very scarce natural element, but nowadays prepared synthetically, but it is a natural element. I'll tell you up to what the elements are natural, and after that all are man-made in some time. Now this is the first demarcation line, the stair step. On the left of it, these are metals, and to the right of it, non-metals. So the stair step to the right, non-metals, and to the left, metals, and immediate vicinity, which are just attached to the stair step, immediate vicinity excepting aluminium. These are called metalloids or semi-metals. And you know the ODI term for that. I'm deliberately avoiding, not avoiding because I'm hating it. I love it, but I'm just made up my mind. I have decided not to put any ODI term today. Now, except aluminium, which is a metal, all others which are in the vicinity of this stair step, boron, silicon, germanium, arsenic, antimony, tellurium, 1, 2, 3, 4, 5, 6. Aluminium is not a metalloid, it is a metal. 1, 2, silicon, germanium, arsenic, 4, antimony, tellurium, 6. And if you include this polonium, you have to also include astatine, so there is no need. These are scarce elements, and they are, you know, they're radioactive, unstable elements. So these are the 6 guys. Some of them lies on the metal side, having more metallic property, but some non-metallic property, which makes it a metalloid. And some of them lie in the other side, the non-metal side, like silicon, like arsenic, like tellurium, but they have some metallic character. So these 6 elements are distinctly called metalloids or semi-metals. Now, these are the 2 liquid elements. This is a metal, and bromine is a non-metal, having formula Br2. It's a diatomic molecule, stable diatomic molecule. It's a red liquid at room temperature. But in India and in Africa and some countries where the climate is the average temperature is about 30 and more, maybe 40 sometimes, then these elements, rubidium, cesium, francium, these as well as gallium, these are also treated as liquid elements. Rubidium, very interestingly, its atomic number is 37, and its melting temperature is also near 37. So when you hold a rubidium in hand, don't do it, lest you will lose your hand. It's very, very strongly active metal. You know how explosive reaction of rubidium with water. So don't do that. You put it over a glove. You wear a glove, and put rubidium, then cesium, francium is radioactive, you won't get it anywhere. Rubidium, cesium will melt on your hand, on your palm, because your body temperature is 37, nearing 37. So when you hold these two metals, rubidium, cesium, and gallium, they will melt because their melting temperature is below the body temperature. So many of the countries, they treat them also as liquid elements, but in Canada, in UK, in Northern America, they all consider only two: mercury as a metal liquid and bromine as the non-metal liquid. And this is 81, 82. I have not completed 83, 84, 85, 86. I have not. I think you have also completed all the atomic numbers in the P block. If you haven't, do it. Now, what I was saying is beyond bismuth, you find all elements are radioactive. Polonium, astatine, radon is 86, then 87, francium, radium, and actinium, and then all the 14 other actinoid elements, thorium, protactinium, praseodymium, all these up to lawrencium, all are radioactive, and also the Rutherfordium, dubnium, seaborgium, borium, hessium, and so on up to this. So out of all these, up to uranium 92, this is 90, 91, 92, the elements are natural, nature made up to 92. And the post-lanthanide element, post-uranium elements is called transuranides or transuranic elements, 93, 94, 95, up to 118 and 119 so-called unenium. All these are man-made synthetic. Up to 92, God-made, I mean, nature-made. But some people, they do not consider the scarce element which are almost extinct, like technetium and one of other elements which belong to the, so this element promethium, that is promethium, it comes here somewhere here. It is also radioactive. So this promethium, which also is radioactive, has an atomic number of 61. This is an exception, which is radioactive. And I'm sorry, I give a different sign. And this technetium, give a different sign. The technetium, you will find it is 40, 41, 42, 43 is technetium, it's radioactive. And promethium is 61, is also radioactive, although they are below 83. Above 83, all are radioactive. Till uranium, all are natural. But some people exclude technetium and promethium, which are now almost extinct in nature. So they say 90 elements. Some of them also exclude other rare elements like francium, which is almost scarce. Some others, radon, astatine, polonium, these are scarce elements. So some people call 88, some 90, but I say 92 I include, even if the availability, natural availability is scarce, low, let us include them in counting. Now in that case, I also include, the neptunium and plutonium. They were natural, but they are also extinct. So 94, I can dare say there are 94 natural elements. In fact, neptunium and plutonium, they are almost extinct, but they were there. They were there because their family members are existing. You will study in your nuclear physics that the neptunium family, the plutonium, their family members are living, but the Bhisma great-grandfather is no more. Let me, you allow me to tell, to use a Odia term, Bhisma Pitama. He is not living, but he was there at his time, but now he's almost extinct. So this is the controversy that you find in several books. Some authors say 92, some 90, some 88, and some 87, and I say 94. Just to raise fun, I include neptunium and plutonium above uranium. They are also extinct, but they were there. They were very much there in the nature. Now, let us study, and the gaseous elements are not many, 11 gaseous elements, oxygen, O2, F2, and all the noble gases are gases. Noble elements, helium, neon, argon, krypton, xenon, radon is radioactive. These are all gases. And fluorine, oxygen, nitrogen, chlorine, bromine is a liquid. So 1, 2, 3, 4, 5. And hydrogen, helium, and all these 11 gases. 2 liquids. I'm not counting the other liquids which are temporarily, even in India, in the cold days in December and January, you will not find gallium and rubidium, cesium, francium in their liquid state. They are solidified. Out of them, rubidium is the highest, 37, cesium is 29, so also gallium is 29, around 30, francium is still less. Now, what we will study, we'll say periodic properties. As you know, the modern periodic law tells that there is a gradual change in the physical and chemical properties. While you move from left to right in a period, you will find a gradual change in their behavior. And when you come down after finishing a particular number of elements in the period, you come down to repeat similar element, which will fall in the same vertical column, what we call group. So the physical properties, the physical and chemical properties are periodic functions of their atomic numbers. That's, I said it, 8, 8, 18, 18, 32, and 32 in the P block case, another 32. So these are the period, the number after which the next element is a repetition of the first element. Say sodium is 11, or say lithium is 3, then after 8 elements, the 11th element, add 8 plus 3 is 11, that is sodium. Another add 8, gain a repetition of the same family, potassium, 19. So it is the periodic function of their atomic numbers. Now we will discuss few of their properties, few of the physical properties. It's called periodic properties. We'll first talk about the atomic and ionic size, then ionization, energy or enthalpy. The good name of energy is enthalpy. If it is heat, then it is enthalpy. Energy is a general term, but if it comes in the form of heat, then the energy will be called enthalpy. So you can call energy problem. Then we talk about electron affinity. This is truly called electron gain enthalpy, electron affinity, but still electron affinity is a very popular term. And this electronegativity. Then others will follow in a very hasty manner, like melting point, boiling point, how they vary, then a density. Of course, this will take oxidation state, that is valency. And of course, the nature of oxides. So I'll be discussing in a super fast speed. Bullet train, I think, has not been introduced in India, as our Prime Minister was supposed to usher in the bullet train concept in India, like Japan and other developed nations. Let's see how, when it comes. I don't know if a bullet train is already introduced in India. Please correct me if I'm wrong. No, how, let's see how atomic size varies. Atomic size, when I say atomic size, I mean a particular radius called covalent radius. Well, metals, they do not form covalent bonding, they form ionic bonding. So their radii, they were called metallic radius. There was another radius called metallic radius that was meant for metals. They do not form any covalent bond, but later a computer simulation was done to find out the covalent radius even for metals, to have a homogeneity and in comparison, in comparing their sizes. So all the radii are covalent radii, although for metals they have been simulated from their metallic radius, which is little different from their covalent counterparts. Now, even the noble gases, which were in our times when we were students, noble gases were not found to form any compounds. They are having stable octet configuration, or helium is still more stable duplet configuration. So they were not giving any compound to measure the radius. In fact, what happens really is to measure the bond length. Say nitrogen molecule, nitrogen nucleus to nitrogen nucleus, that is the bond length. That can be measured by some techniques, what we call the X-ray diffraction technique. We can really find the bond length. And half of that will be the radius, the covalent radius or atomic radius. In general, we call atomic radius. In particular, we call covalent radius. Earlier for metals, there were metallic radius, and for gases, there were also another bogus radius called van der Waals radius. Now it is looking bogus because they do not give the actual size of the atom. The atoms were not bonded, but rather they are close in the solid state, but they are not bonded. So the internuclear distance between two non-bonded atoms, even in the solid state, is not a true representation of its size. So when noble gases have started, producing compounds, they could measure the bond length and simulate, and then find the covalent radii. So what we will discuss is the trend, how the covalent radii, which represent the atomic size, they vary across a period and down a group. So covalent radius in period, it decreases, and in group it increases. In a period it goes on decreasing. If I show you the data, you will be very happy, because I will make a data analysis to tell you how it changes. These are the atomic size. You have a look. Lithium is 1.34 angstrom. These are in angstrom unit. 1 angstrom is how much?
10
It's
to the
10 power -8. Oh. What has happened?
Sir, -10. Sir, -10. 10 to the.
Yeah. I was here, somewhere here. Yeah. And something happened. 1 angstrom is 10 to the power -8 centimeter, or 10 to the power -10 meter. So most of the time you calculate in centimeters, so 10 to the power -8 centimeter. So in terms of angstrom, you find in a period, say we select the second period, 1.34, 0.9, 0.82, 0.77, 0.75, 0.73, 0.71, 0.69. Even the noble gas following fluorine has a lower size than fluorine. But in our time, when we were studying, we are told, and in the book, the table that we were using, you find this is much greater than fluorine. Maybe it is similar to this or this lithium. Because at that time, the noble gases, the scientists did not have the covalent radius. It was a van der Waals radius, which ought to be much greater than its real size. So we used to study up to fluorine group 7A, it decreases, and suddenly in the group 0, noble gas, it increases again. But we used to say these were covalent radius and this is van der Waals radius. The increase is not true. It is a fake increase because its van der Waals size does not give a proper knowledge about its size, proper idea about its size, while all others, they represent the correct size. So you will find in third period same. But in a group, if you notice group 1, you will find they are increasing, going fatter and fatter, bulkier and bulkier, 1.34, 1.54, 96, 2.11, 2.25. And also, but this red zone, this transition series, we have several anomalies, which you will study in details in your class 11 program. If you don't find anywhere, do not forget to open my periodic classification for class 11 program. I have extensive discussion for every physical property. One lecture, 1 hour, maybe more than 1 hour lecture is dedicated to atomic size. Then maybe 2 lectures for ionization enthalpy to unravel the mysteries, the anomalies in the entire DBlock. And the bottom portion that we have drawn the bottom portion of lanthanides and actinides. These are called the bottom portion. So the detailed analysis and their anomalies will be discussed. You find that in any transition series, the change is not discernible. It's not very, very large. It goes on decreasing up to certain element and then remains more or less same. And towards the end, it increases a little. Now we will discuss, and you will know the reason behind it by getting 2 new concepts, what is called the screening effect or shielding effect vis-a-vis the penetration effect. So the nuclear attraction, the nuclear pull, they go on changing. Because you will find the last electron in all these cases from scandium to zinc are entering into a d orbital, a 3D, while the last cell, 4s or 5s for the second series or the 6s for the third series, remaining fixed. The differentiating electron means the successive electron which enters the d orbital, and that electron distinguishes that element with respect to its preceding element. That is called the distinguishing electron. Differentiating electron, I'm sorry, enters into a penultimate cell's d subcell, while the ultimate cell is responsible for the size, for the ionization enthalpy, everything. The last cell is responsible, but the electrons are being added in the previous cell, so which contributes shielding effect, screening effect. So it doesn't allow the nuclear pull to build up more drastically. So the nuclear addition of a proton in the nucleus, an addition of an electron in the inner cell, in the penultimate cell, these 2 effects are opposite to each other. The proton in the nucleus wants to attract the outermost 4s or 5s electron, but the intervening electron acts like a shield or a mechanical barrier to obstruct the relationship between the nucleus and the outermost electron to reduce the nuclear pull. So they almost cancel each other, and as a result, the variation in the atomic size is not much. In the beginning, it is detectable, 1.44, 1.36, 3 elements, where the screening effect is not much pronounced, but then the screening effect takes the lead to sabotage the nuclear attraction. And we'll know towards the end it will increase. Same thing will happen here. And but there are several anomalies. We'll not discuss about that. Usually up to class 10, we talk about these S block and P block, which are together called normal elements or representative elements. And these are maddening elements. I'm just funnily saying this contains a lot of anomalies. The D block and the F block contains a lot of anomalies. So even in the electronic configuration that we studied only for chromium and copper, 1 electron is exchanged between the NS and N-1D. In the second series, between 4s and 3d, in the second series, you will find so many anomalies when 1 electron is exchanged. Starting from niobium, molybdenum, technetium is an exception. It follows the Madelung's rule. Then ruthenium, rhodium, and in palladium, you'll find 2 electrons from the 5s go to complete the 4d10 configuration, and 5s is 0. You will be astonished and you will be told about the possible reason behind this. And silver is again like copper is fulfilled configuration 5s1 4d10. So in the third series you have no anomaly, even in tungsten, which is falling below chromium, molybdenum for showing half-filled character, half-d subcell character. Such stability factor is missing here. Tungsten, it will be 6s2, 4f14, 5d4, not 5, not 6s1, 5d5. Now, here the anomaly starts from platinum, 1 electron exchange, and gold as usual. So these two are the anomalous electronic configuration. And in second series, you have niobium, molybdenum as usual, like chromium, ruthenium, rhodium, 1 electron shift, palladium, 2 electron shift, silver as usual, copper, silver, gold, 1 electron shift. You'll know the anomalies. Then coming to ionic size. Now, let me ask you how many of you are comfortable when I am speaking in English. Raise your hands. And you do not want me to come to change the mode of my talking from English to Odia. Who wants me to continue with the same language I am doing? So, well, Ipsita, Pritham, they want me to talk in Odia, but please bear with me, Ipsita Singh. I don't know whether you are uranium awardee or you are an invited, because we have invited everyone to join even the Zoom program. So you are one of them, or maybe you are a teacher and you are watching us how we are going. I have also invited all teachers teaching in schools to have a watch on our discussion. Now coming to ionic radius, ionic size, let us write down in our, because I'll send you these files and also the data. The ionic size is very interesting. Always the cationic size is less than the atomic size. And also, you will be learning another new term called effective nuclear charge. Effective nuclear charge, you will also calculate from the atomic number, the real charge, minus the screening constant, how much charge is being eaten away, is stolen away by the screening effect. And there is a rule, the Slater's rule, to find out the screening constant. And you will subtract that from the atomic number to get the real, the charge that the outermost electron is really experiencing. Not that it is present, I have 1 crore rupee in my bank. But the outside people will not know unless I spend them, either for myself or for others. Nobody will know. So sodium will not know that there are the last electron of sodium 3s1, that will not know that there are 11 protons. If you ask the last electron, how many protons do you think must be there in the nucleus? He will say, yes, I'm sorry. You will tell number of protons is 11, then he will be astonished. The last electron, the 3s electron, will be surprised. Oh, 11 protons? I'm not experiencing that. I'm experiencing only 7 or 8. I will calculate, or maybe 5, maybe 4. I feel as if there are 4 protons. That is the effective nuclear charge. That is a governing factor to decide everything and anything in periodic properties, which I will not have the time. We have left with 15 more minutes to wind up. And doesn't matter when you grow to the class 11, I'm not going anywhere. Keep in touch with me, and whenever you find difficulty in chemistry, not physics, because my limitation is up to 10. I have kept myself prepared to tackle questions up to 10 and to teach also physics up to class 10. I don't have my expansion of my experience in physics with class 11 and 12, because I don't study them. I could have done that, but I don't find time to do that. So in any chemistry problem you encounter, feel free to write down in WhatsApp, in your personal WhatsApp, because this group will die after our group is over. Our exam is over. After a month, maybe 1 more month, we can sustain that group. After that, all of us will be defunct. Either you leave or may not leave. It will be buried down in our WhatsApp list and will not be resurrected unless someone will play a mischief of sending some message or some forward message. Nowadays, we are fed up with the forward messages. Whatever, picture, videos that you find and you like, you don't feel not to send to your friends. Immediately you decide, since I am happy, since I am pleased to watch the video or the picture, my friends should see it, Don't do that. Don't do that. Don't be a philosopher to teach philosophy, spirituality to others. Apply to yourself. Others are also equally prompt. Don't send any forwarded message to anyone. And also nobody should forward any message to you, unless it is of your study related or your your career related. Now, this thing will not happen to you because you are still young. But as you grow, you will find you will have so many WhatsApp groups. Your school, class 10, plus 2, plus 3, plus 5, plus 9, so many WhatsApp batches. And, as you grow older, you will find the guys have no time, only time to play with their smartphones and forward message, write something, mostly forward message. They don't have time. So if you are busy, then you would get time to even to look at what others are sending to you. You'll be disturbed. A bip will come and will be. Okay, coming back to cationic size is always less than the respective atomic size. For you, I will explain it in a very rudimentary way. For example, sodium plus is less than sodium. If one electron is removed, but the proton inside the gut, inside the stomach, remaining same 11, only the outside electron, one electron has been removed. So the nuclear pull increases and therefore the size decreases. There is a shrinkage in the size as the number of protons remain the same, but the number of neutrons is reduced. But later on, you will find it is the effective nuclear charge which increases while you remove one or more electrons from a neutral atom. Similarly, Mg2 plus or Ca2 plus is less than Ca plus, which is unattainable, I told you, which is less than Ca. I told you that once one electron is lost, the second electron will never spare. It will be jumping up its own. But had you, with so much of caution, yes, there are methods where you can selectively you remove one electron, keeping the other electron, then you'll find progressively the size will increase. The least size is that of Ca2 plus, then followed by Ca plus. Similarly, you will find that anionic size is always greater. Than atomic size. When I say atomic size, I mean covalent radius. That means chloride ion is greater than chlorine atom. Say oxide ion is greater than oxide 1 minus, which is unattainable, but we can, which is greater than O. So as more and more electrons are fed into a neutral atom to make it a negative ion, the protons remaining same, the number of electrons increases, so the nuclear pull decreases. When the nuclear pull decreases to the outermost electron, there is an expansion in size, the size increases. But you will study later, the effective nuclear charge decreases by the addition of one or more electrons. So I will show you the data to see how much change it happens when one electron is removed, to compare between. Now see, this was the data I showed here. This is the atomic size, the covalent radii. Now coming back to ionic size, yes, cation and anion size, you see sodium was 1.86 here. You remember, sodium was 1.54, and remember chlorine was 0.99 as neutral atoms. But as ions, you find that sodium ion is 1.02. It was 1.54 when it was a neutral atom. Now sodium ion is 1.02. And look to chloride ion, it is 1.81. It was 0.99, nearing 1 angstrom. Almost doubled, almost 1.81. So by feeding one electron, you become a fatter guy. I can't say guy, girl. Non-metals say we call girls, and metals boys, or don't, if you are a girl, don't take it otherwise. Just I'm kidding. Metals are larger in numbers, so the girls are, I mean, the non-metals are lesser in number. So also in the population, you find the girls' number is decreasing. It is little less than the boys' number because of, you know, the reason, you know. This is not that different, you know, in case of metals and non-metals. There is a huge difference between the number of metals and number of non-metals. Number of metals is so many in the left side of the stair step, and number of non-metals is so less. And you know, then we talk about ionization enthalpy. That's very interesting. That's very interesting. Well, we will be spending a little 10 minutes more time today, maybe 5 minutes more time today. Ionization enthalpy. It's very interesting. We simply call it IE. It is the energy which is required to pull out the outermost electron. Say you have in the gaseous state from the atom. Supposing you have a metal or any element X in the gaseous state as an atom and an individual atom, and you remove one electron and it becomes a positive ion in the gaseous state. And let me do something. Let me write the energy here because it is absorbed. Unless you supply some energy, you cannot knock out the electron. So electron, let me write down the electron in the right side. So the amount of energy which is needed, which is absorbed by a neutral gaseous atom to lose one electron from its valence shell, that is called the ionization enthalpy. In fact, it is called the first ionization enthalpy, the first electron. But you can remove the second electron, which is much more difficult. Because once a positive ion is created, to remove a second electron from a positive ion, to overcome the attraction between an electron and a positive ion, the effective nuclear charge still increases. So it is still more difficult. This is but possible. This is called IE2, second ionization energy. And then the third electron, third ionization energy, which is still greater. So let us talk about when we say IE, it means IE1, the first electron. Now, let me tell you the trend. In a period, it increases, just the opposite of the size, the covalent radii. As the size decreases, because the nuclear pool increases, the effective nuclear charge increases, as you will see later. And we fool the school level, class 10 level or less level students by saying that in a period, the protons are added to the nucleus and the electrons, they remain in the same cell. They do not change to higher cells. And in a group, the last electron enters into a higher cell. 3s1, 4s1, 5s1. Therefore, the size increases, the nuclear pool decreases. We just pull them. Particularly in a period, we don't say anything. We say that the successive electrons are filled in the same cell, while one more electron is added to the nucleus. The electrons are not going away from the others, going away from the same cell, remaining in the same cell. So the nuclear pool, then we pull, the nuclear pool increases, size decreases. But later on, you find the effective nuclear charge really increases across a period for which size decreases. And across a group, in fact, effective nuclear charge remains the same, because the nuclear attraction depends on two factors. You will find one is the effective nuclear charge, the other one is the distance factor, the R² factor, the Coulomb's law of forces. So since the radii, the distance of the nucleus from that outermost cell increases, so therefore the nuclear pool decreases, size increases. You will know that later. But coming to ionization enthalpy, in a period it increases the same reason. As the nuclear pool increases, the effective nuclear charge increases, becomes increasingly difficult to pluck out one electron from the outermost cell. So energy invested becomes more and more. In a group, it decreases. As the size increases, the nuclear pool decreases, it becomes increasingly easier to pluck out the outermost electron. So the ionization energy decreases. Let me show you the data. Once I show you the data, you will be really, really happy, I'm sure. This is the ionization. When I say ionization energy, I mean first ionization energy, the first electron. The comparison you find in second period, you get a hump. Although the main trend is increasing, but you will find a hump, just like in cities like in India, you go anywhere, in a 50-meter distance, you will find a hump. That's not a regular hump, it's a man-made hump, and that hump sometimes will put you in grave difficulties and accidents, like a mountain. The local people do it to slow down the guys who are little heroic, and they whenever they see population, some heroism develops in their blood, they increase the accelerator speed, and they might cause any problem in the vicinity. So they make mountains in the name of humps. So you will find a hump in group 2. I'm sorry. And in group 15, you find that, yes, there is an increase between lithium and beryllium, but the increase is so much so that the next element, boron, is less. Because what we fool to the students, even up to class 11, that this has a full-filled S configuration, having some extra stability, 4s2. This is 2s2, 3s2, 4s2, 5s2. So this extra stability makes it a little more resistant to the loss of electron. So much so that the victim is the next element. Then it continues to increase, and again a hump comes. But nitrogen is half-filled. There are 3 electrons which are singly occupied. Hund. This is 2s2, 2p3. The 2s2 is fulfilled, but 2p3, hund. So 3 unpaired electrons are there. And because of the half-filled stability, we fool the students, saying that since all these have half-filled stability, becomes a little more resistant compared to the succeeding element, so that oxygen has a lower IE than nitrogen. Then it increases. Neon, the respective noble gas, has the highest ionization enthalpy in the respective period. Then suddenly there is a drop, because once you come to an alkali metal, then you are removing from the outermost shell, which is S1. The nuclear pull is much less. Size is much greater. Nuclear pull is much less. So although it is less, in a group it goes on decreasing. Lithium was 520 and sodium is 496. It goes on decreasing. But the same anomaly, hump, you will find while go from sodium to magnesium, there is a drastic increase, but aluminum is less than magnesium. Then it goes on increasing. Even silicon has greater IE than magnesium, but phosphorus, again, there is a hump. The increase is so drastic that sulfur, the next element, has a lower IE than phosphorus. And then it goes on increasing. Same thing will be found in the 4th period among the normal elements. Forget about these maddening elements. These are mad fellows. You will not find any consistency in the IE along a group, along a transition series. They're high, but it fluctuates. No consistency, but the last element has the highest IE, even higher than its succeeding element in the P block. And you will know the reason when you go to class 11. And you find the same anomaly, calcium has greater than, the gallium has lower than calcium, and selenium is also has lower than arsenic. But the difference has been lessened, reduced, so much so that such hump anomaly you will not find in period 5 and 6. So that is absent. Consistently, it goes on increasing, barring the maddening intervening DBlock series, second series, which have inconsistency. We will know more about the variation of the D elements along groups. You will find interesting observation when you study their variation along each transition group. You will encounter a phenomenon called Lanthanide contraction, for which the size remains more or less the same. Titanium, zirconium, talking about the size, it remains, the size table is now not here. You will find the size increases from 1st to 2nd, but in the 3rd, it remains almost the same. But in ionization enthalpy, the highest is for the third element. While for normal groups, it goes on decreasing down. But in transition group, the highest is that for the last element. Forget about these synthetic elements whose properties have not been studied. So the data you will not find anywhere. So it goes on changing. First to second, it decreases. But the third is the highest. Can you imagine? That is due to a very interesting phenomenon called the Lanthanide contraction. You will know about that. And here you find gallium is a little more than aluminium. Although in reality, in all other groups in the P block and S block, it goes on decreasing. But here is one anomaly. Gallium has slightly greater IE than aluminium. This you will know the reason is called the DBlock contraction or the Scandide contraction. So I'm showing you the anomalous areas where in the period in a series, this variation is inconsistent. The last element is the highest, but among group, you will find a very specific trend reducing from first to second and then increasing to such a high value that it is the highest. Okay, then we will just talk something about, we are 6 minutes past. I will take 4 more minutes. Electron affinity. We'll take its magnitude only. And when you, particularly it is valid for the negative, and the non-metals. When in the gaseous state, you feed one electron to make it an ion, negative ion in the gaseous state, you will find the reverse phenomenon will happen. Some energy will be released, some heat energy will be evolved. So that is called the electron affinity. So by gaining one electron, it is losing energy. So that magnitude of energy lost is called electron affinity. Many metals, they do not, even noble gases, they do not, lose energy to gain electron. They are like very obstinate guys. Their mothers feed them with a stick. One gulp, one stick. So that, this will come to the left side. It will be an endothermic process, but we will be talking about those elements, mostly the non-metals, which easily accept electron by evolution of energy. But the exception is nitrogen, which is small in size and half field configuration. It doesn't have a desire to eat. So a nitrogen's mother, her mother feeds with a stick, gives one gulp with one stick. So you will find in case, if you take the magnitude only for those which evolve energy, the trend is similar to IE. This is called EA. And among period, it increases. And among groups, it decreases. The trend is similar to. Right. I will show you the data. Unless I show you the data, you will not satiate your, your strong urge to know more and more. Some of you are really, this is electron affinity. For those elements which do not have a tendency to accept electron and do not produce any energy, they need the feeding with a stick by their moms. In that cases, we have written 0. That doesn't mean that they will not gulp electron, but with a stick. Those values which you find, these are, those elements which gulp electron, which take electron with evolution of energy, with exothermic process. You'll find there is an anomaly where lithium, though a metal, since it has only one electron, it wants to pair with another foreign electron, so it gives energy. But this is fulfilled, 2s2, 3s2, so it doesn't have a desire to gain electron. Lithium, since it is a metal, you can't compare with a non-metal, metalloid. It suddenly decreases, but thereafter it increases. But nitrogen is 0. It doesn't have a tendency. Don't compare nitrogen. And of course, neon has no tendency to gain electron. It can gain with a stick. But in higher stage, in class 11, you will find everything. Those things which I have shown you with only the figures, they will be given minus sign, because the exothermic process will be shown a heat change with a negative sign, and endothermic processes will be a positive sign. So all these you will find data along with nitrogen, and these all the elements were written 0, you will get data with positive sign, and all others given only the values will be found the same values with negative sign. But for now, let us not complicate the matter. So in a period, it goes on increasing with selective elements. Down the group, it decreases 60, 53, 48, and so on. Now, before I close, really, I want to talk about electronegativity. And let me just put a word on electronegativity. It is the tendency of an electron. Supposing you have an electron pair in a covalent bond. So it is the tendency of an element X or Y to attract the shared pair of electron towards itself. Supposing the shared pair is close to Y, then this is more electronegative. Electronegative. And this is less electronegative. So this is not the tendency to gain electron, that is electron affinity, but the tendency to attract a bond pair or a shared pair closer to itself. More the attraction to, more the tendency to attract the shared pair, more is its electronegativity. So the maximum electronegativity is given to fluorine, which is 4. The second highest is oxygen, 3.5. The third highest is bracketed nitrogen and chlorine is close to 3. The fourth highest is bromine, 2.8. And you will find in a period, it increases. Up to, of course, halogens, then abruptly there is a difference in noble gases. But we say increases. I'll show you. In a group, it decreases. So as the electronegativity increases, the non-metallic character increases. And the nature of the oxides become more and more acidic, less and less basic. Down the group, the electronegativity decreases. As the electronegativity decreases down the group, if you are on the left side, the metallic character decreases. Increases. I'm so sorry. Increases. And if you are in the right portion in the P block, in the non-metallic character decreases, the metallic character increases. More the electronegativity, more is the metallic character. Less the electronegativity, more is the metallic character, less is the non-metallic character. So you will find all this in the data. You will be finding here electronegativity maximum is 4, 3.98 is taken as 4, oxygen is 3.5, and in a period it goes on increasing, and the electronegativity data is missing for noble gases excepting xenon. But nowadays you will find for all of them, because they have started forming their covalent compounds, so that the tendency to measure the attraction. There are so many methods to calculate electronegativity that you will learn in your class 11. And then these maddening elements, they have a very, very peculiar kind of trend, but go down the group, it goes on decreasing. So as it decreases, you will find the metallic character increases, non-metallic character decreases. As you find decreases, even if these are all metals, but still the metallic character increases. And we can't say non-metallic character decreases because we are in the heart of metal zone. So with this, I feel like declaring the end of our 15 days long program, and some of you are watching from YouTube on a live program, and some of you are here with me. So congratulations to all of you. who are with me till the end. So again, I would like to request those who have not yet subscribed to my channel, do so for your good and also for the good of your acquaintances. So whenever I will produce new videos, you can get the notification instantly. So we are there in WhatsApp group, and others who are watching can link with me in my WhatsApp number. You can get me in our website, which is www.theuranium.in, not org. It is no more there. So you can get me there and can contact with me, and I will let you know the examination time. And today, since I'm leaving very soon, you may not get these files, may not. If they are late, my family members are late, because today is the last day of our program. I have kept one outing program with my family, which I used to avoid. So I'll return back in the afternoon, then I will send you the files. Have a glance to the data and the periodic table. Bye-bye.
Sir, pranam.
Sir, pranam.